So in this session, we are going to see MSSP module. Now this master synchronous serial port can be utilized in I2C mode. Now when you are saying that as a I2C mode, we are aware that uh, there is two mode of operation under the SPI, under the MSSP. That is, one is SPI and other one is I2C. So I2C is nothing but inter-integrated circuit. Now, this particular I2C can communicate with multiple peripherals with only two lines. So, over two lines, the communication will get taken place with respect to the I2C mode of operation. Now, in that manner, this particular I2C mode can be operated in a way of one master, multiple slaves operation or multiple slaves configuration. Now, when you are saying that multiple slaves are there, then there could be addressing of that particular slaves so that individual slave can be identified and addressed with the distinct addresses, isn't it? So, for this purpose, the slave addresses, there are some of the options are available in this I2C mode. Either you can generate 7 bit of address or 10 bit of addressing is allowed for it. So in order to that, you can have a combination of, if at all 7-bit address is there, 2 to the power 7 means 128 addresses it will able to generate. So 128 slave devices you can connect it to one master if at all your address is 7-bit, and if 10-bit address are there, then the possible maximum limit for the slave to get connected with your master is 1024. Clear? So in that manner, let's say your MSSP can communicate over two lines. So those respected two lines for multi-master functionality for communication between your master and slave over SCL and SDA. SCL is nothing but S clock. That is serial clock, and SDA is nothing but serial data. So the data to be transmitted and received has to get taken care by this line. So this signal is for your data transmission and reception, whereas in the communication will get taken place over your serial clock. So the clock will be provided by the signal as SCL. When you communicate with your peripheral, in SPI, actually the communication was only taken care with respect to master and slave. So if at all you wanted to provide, there is no any kind of acknowledgement in SPI, there is no any kind of start and stop bit in SPI. So in short, you can say that I2C protocol will always provide start and stop bit along with the data, and every time it will able to generate acknowledgement. So this acknowledgement concept is missing in SPI, whereas in for the I2C, it is very well sustainable in the case of the communication between master and multiple slaves. So whenever you are going ahead with the I2C communication, it is more preferred over SPI just because of this communication and multiple slave configuration that will get connected with your master. Now, whenever you are initiating the communication between your master and slave, every time it will works around on the basis of acknowledgement. Let's say you have initiated one slave. So slave address you need to configure it. So again that configuration with the multiple slaves, it is being accepted. So whichever slave is fixed and utilized with that same exact address, that slave will send an acknowledgement for the address. After address acknowledgement, again there is a acknowledgement, master will initiate the start bit, and along with that data will get initiated. So every after transmission that will initiate it from master, uh, your slave has to respond to that master in the form of acknowledgement. That's why the more secure communication in I2C is being observed over the year. Now, when you are going with this particular MSSP in I2C mode, again, of course, there is a write sequence and read sequence. Means there is a transmission sequence as well as there is a reception sequence. So, in order to that, all the time, be it with the transmission or be it with the reception, let's say we'll initiate this as a from master side. So, write sequence, the one which is highlighted in blue is nothing but master to slave communication. So in order to that, whenever you wanted to communicate from your master to slave, you need to initiate with the start. After the start, you need to provide the slave address. Now the sequence of if at all your system is having multiple slaves altogether, these slave addresses will be accepted by all the slaves in the configuration, and whichever slave address is being matches with this particular slave address initiated from master, that slave will get active. So in order to that, the slave address will be active, and as you wanted to generate this as a write sequence, so you need to provide this r/w bar as a 0, means it is in the form of write sequence. That's why it is active low. After that, after initiating the start and slave address, there has to be response to get initiated from slave to master, and that is nothing but acknowledgement. So whenever acknowledgement is coming in, at the time your SDA signal will activated as a low, and when there is a no acknowledgement, then at that moment your SDA signal will be initiated as a high. So even though if at all you wanted to monitor whether the master have received acknowledgement from slave or not, that will be indicated from this particular A bit in the form of active low or in the form of active high signal. If at all, let's assume that we have received acknowledgement from slave. So now your master will ready to initiate your data. So now the data bytes will get transferred to that respected slave. And as you are transferring your first packet of data, again your slave needs to send an acknowledgement to the master as a data acknowledgement. And then afterwards, again similar to that your previous data packet, your master will send again furthermore data packets to your slave. Like this way, multiple datas can be transferred over the same sequence of write sequence from master to slave. So every after transmission, be it with your slave address, be it with your data, every time your slave has to respond to the master in the form of whether acknowledgement or no acknowledgement condition for it. And there at the end, there could be a possibility to add your stop bit. So P is nothing but your stop bit. So this is nothing but write sequence for your MSSP module. Now similar to your write sequence, again there is a read sequence. Now for read sequence, same kind of stuff is going to get happen, where start condition is initiated, slave address is being given. Now in that manner, whenever you wanted to read, this signal has to be 1. So unlike this, as you wanted to write the particular data in that manner, this will be considered as a 0, as a in the mode of write, whereas in for read it has to be 1. And after that, there is an acknowledgement from your slave address from your slave to that respected master. Then you are initiating the data reception. So these data bytes will be transferred from your slave, because this is read sequence. So here the data will also be sent from your slave to master. So in this communication, again there is a condition of transmission. Your master can transmit, master can receive. Whereas in for your slave condition, again slave will be in follow in the form of two ways. slave can transmit, slave can receive. So if at all you wanted to, your slave wanted to transmit some data to master, so it will initiate that respected data, and slave address is mentioned into that respected frame. That's why it could be easier enough to identify your slave address from the multiple slave device that are connected with your master. And again, as you are sending this data from slave to master, then acknowledgement must be given from master to slave. That's why it is highlighted in blue. So blue color is nothing but acknowledgements that are being received from master to slave, and the one which is highlighted in white color, that is nothing but the condition which is mentioned from slave to master. And like that way, multiple data packets you will able to transfer from slave to master with respect to the acknowledgement, and at the end you will mention the stop condition. So this is the generalized write sequence and read sequence in MSSP I2C mode. So this is more in detail for I2C protocol, what could be the particular packet contents and its size. So let's say here, every time you wanted to transfer your data frame, multiple data frames will able to attach in your protocol, but the size of data frame has to be 8 bits. In the form of every data frame, acknowledgement and no acknowledgement bit is appended for each of the data frame. Then and then only furthermore next data frame will get initiated. So whatever number of data frames are there, the size is 8 bits, and along with that there is a possibility to append the acknowledgement for that respected bit, be it from master to slave or slave to master transmission. And at the end you will able to provide one stop condition. So there is a start and there is a stop, and in between that frame there is a slave address. So there is possibility of to generate two categories of slave address, either 7-bit slave address or 10-bit slave address. If at all 10-bit slave addresses is there, then 2 to the power 10. It will give you 1024 addresses. So in short, you can connect 1024 slaves to your master if at all you are initiating the 10-bit address. Whereas in other option is there, you can generate this slave address of size 7-bit. So 2 to the power 7, nearly it will give you 128. So 128 slaves are connected to your master. This is one kind of justification to this address frame. So this is address frame, this is data frame, along with that start and stop condition with the acknowledgement and no acknowledgement condition. So this is the generalized frame format in MSSP in that too within I2C mode, specifically I2C mode. So this is block diagram for I2C. Now to program this I2C, again some of the registers are required for it. Now these register may be the, as you are enabling this particular I2C operation using MSSP module. So you require 6 registers for I2C operation. And those are, let's say first register is SSP con register, second register is SSP con 2 register, third register is SSP stat register, and fourth register is SSP buff register along with the shift register, which is nothing but associated with your buffer register. And sixth register is MSSP address register. So the slave address has to be mentioned with the help of MSSP address register. So in order to that, this particular address register holds either 7-bit address or 10-bit of address for your slave, and that is being masked with your address mask register. So all the time, if at all you are connecting with the multiple slaves altogether, so these two lines is connected with the multiple slaves, let's say slave 1, slave 2, slave 3 and so on. So because the communication is over these two lines only, SCL and SDA, isn't it? So for all the slave connection to your master over these two lines only. So all the time out of your multiple slaves, every time these kind of addresses will accepted from all of the slaves, but only one particular slave will respond as an address match. Out of that, whatever multiple slaves are connected in your network. So in that manner, if at all address is matched, so in that manner either you can transmit and receive the data over this SDA line through your internal buses. Read and write operation can be performed with your data. So the data to be transmitted has to be mentioned in SSP buff register, and this SSP buff register is associated with the SSP SR register. So in order to that, this particular SSP SR register will help you to shift that particular data serially over your SDA. So in that manner, if at all you wanted to transmit that data, the write operation will get initiated, and like that way the data which you wanted to transmit has to be loaded in this particular buff register. Till that time you could able to send and specify the address for it, and due to which the condition will be mentioned for the transmission. Other setting like reset bit, start bit, stop bit, that is mentioned in the SSP stat register that will get associated with SDA and SCL. So here you can conclude this by saying that SSP con 1, SSP con 2, SSP stat register are the control register and the status register in I2C mode of operation. So the SSP1 and SSP con register are readable and writable. In order to that, the lower 6 bits of your SSP stat registers are read only, and upper 2 bits for that SSP stat registers can be either readable and writable. Clear? So here the SSP add register. So you can conclude by saying this SSP add register holds the slave address when the MSSP is configured in I2C mode. So when MSSP will be configured as a master, the lower 7 bit of SSP add register that will act like a baud rate. So this baud rate will be the rate of communication between your master and slave, and that can be loaded in the form of the some kind of values altogether. This is all about the transmission. What will happen in the reception? So in reception operation, SSP SR register and SSP buff register together to create a double buffered receiver, just like the case of your SPI. When your SSP SR receives the complete byte, in that manner, it is being transferred from your SSP SR, and then in the form of interrupt will get generated because the reception is being completed. But during the particular transmission, this particular SSP buff register can't get double altogether, and it cannot be used as a double buffer altogether into it. Now, what are all those steps are required for I2C transmission? Now, very first step is to send your master to send with the start condition as per the data frame format size for the protocol for I2C protocol. We are initiating with the respected start condition. So, every time it has to be connected with the start condition by whenever you are giving the start condition, it is considered as SDA line on that particular I2C from high voltage level to the low voltage level switching will be initiated. So in that manner, before switching that S clock line from high to low, this can be initiated. After that, there is a transmission of your slave address, and that is being initiated from your master. So the slave address of size either 7-bit or 10-bit address will be there. So for to communicate with it, you can again mention the whether you wanted to communicate or whether you wanted to provide the reception in the form of transmission or in the form of reception. This particular read write bit is associated with that respected slave address. What will happen if you have initiated that slave address? In third step, each of the slave will simply compare the address that is sent from your master. Now this comparison will simply address one kind of address match condition from your slave, and whenever the address match is occurred here, in that manner it will generate one acknowledgement from slave to your master. So once your master will receive that respected acknowledgement, then it will able to generate some kind of master, maybe either send your data frame or receives data frame from that either slave or to the slave. In that manner, the master will initiate the transmission of your data frame or reception of your data frame from slave. But here in fifth condition, if at all you are having multiple data frames all together, each data frame has to get transferred and must be received one kind of acknowledgement bit either from to or from your master. And after the successful transmission for whole of the data frame, there is again transmission of the stop bit. So this stop bit condition will identify that transmission is completed successfully, and initiation of the end of communication will get initiated. So like this way, your I2C transmission can able to establish with the SDA and S clock pin. Now, as I have told you earlier that slave addresses with respect to that 7-bit slave address will generate unique addresses 2 to the power 7, nearly 128 addresses it will generate. Similar to that, if at all you are using 10-bit addresses, in that manner this is very uncommon, but still if at all your slave, if at all multiple devices you wanted to connect with your master, then maximum limit is 10-bit address. So in order to that 2 to the power 10, it will provide 1024 unique addresses for your slave. Now let's take this as a I2C advantages and disadvantage over SPI. Now very first advantage, there is only 2-wire communication over only 2 lines SDA and S clock. So it uses only 2 lines of I2C, whereas in for SPI it utilizes 4-wire communication. So those 4 wires are, just quickly revise you that 4 wires are nothing but SS, SDO, SDI and SCL. So through that 4 wires communication will get established, whereas in for I2C only 2 wires are required for communication. Now here again your I2C supports multiple master with the multiple slaves option is there. So in order to that, this multiple configuration can able to establish with the multi configuration of your slaves and masters all together. Now there is a again third advantage is there is a kind of acknowledgement concept in I2C protocol. So every after single transmission and reception, acknowledgement has to be given from your slave or from your master side. So in order to that, there is a acknowledgement, it will simply give you some kind of confirmation, whatever you have initiated from either of the side, that is successfully received to the other end. Fourth will be the hardware. So hardware which is used here is less complicated than your UART. Because in UART, what is the condition? You need to provide max 232 because there is a level shifting, level voltage current shifting between two of the different nodes altogether, and then you are initiating with the DB9 port for this RS232 serial communication. Like that way, the hardware become complicated with respect to UART. So here there is no any kind of complication, only pull-up resistors is required for them. If at all you are connecting the multiple slaves all together to your master, then and then only pull-up resistor is been associated with these two lines SDA and S clock. Now this protocol, because of this acknowledgement, it is most preferably and appreciated in widely application in all the embedded system. Whereas in again, even though that is some of the disadvantages are there for this I2C, maybe the slower data transfer rate than that of your SPI. There is a data frame size limitation of only 8 bits. So all the time you have to split your multiple datas all together into a chunk of block of code of size 8 bits. So 8 data frames, you have to split your whole data into 8 bits, and likewise you can transfer that respected data frame. So there is a limitation of data frame size, and some kind of a more complicated hardware needs to implement than that of the SPI, because here you need to monitor the pull-up register. So again, according to that, you need to check the particular two line signal SD and S clock that has to get associated with the respect of reference voltage levels for that respected pin. You have to monitor. That's why it becomes a little bit complicated than that of SPI. Now in MSSP, under the I2C mode, registers are used. So out of that, let's say SSP start register. Very first SSP start register is status register. Now in this status register, all the time you can consider the same register is being used in the SPI mode, but little bit changes are required for it, and those are, let's say, your master SMP bit. So this SMP bit is nothing but uh, master or slave mode slew rate control. So there is a configuration setting for this particular speed of communication with your master and slave. With the standard speed, if at all you are mentioning is the communication speed is nearly 100 kilohertz and 1 megahertz, whereas in if you provide this as a 0, the speed becomes 400 kilohertz. Next bit under this is CKE. CKE is nothing but SMB bus select bit. Now this SMB bus select bit is nothing but in master or in slave mode you can utilize this. But when you put this as a 1, your SMB bus will be provide specific inputs, whereas in if you provide this as a 0, it will simply disable the inputs from CK. Next, as you are initiating the slave addresses, so under this respected instead of SPI, this is I2C. So in I2C, data and addresses are indicated. So in that manner, this particular data addresses is nothing but if at all you are using under the master mode, it is reserved. Whereas in for the slave mode, one indicates that last byte received or transmitted was the data. And when this particular bit is 0, which is nothing but it will indicate that the last byte received and transmitted, that was an address. So this particular data transmission condition or address transmission and reception condition is only valid in SPI mode. This is not there in master mode, slave mode, not SPI, this is slave mode. But this condition is not there in the master mode. Next is start and stop. So this start and stop bit is absent in SPI, but whereas in these two can be utilized in I2C mode, because in your frame format of I2C there is a S and P bit. So this is S and this is P. So S stands for start, P stands for stop. So in order to that, this SNP bit is nothing but to initialize the condition of your start and stop in I2C mode. Next, condition of your read and write. So in that manner, again there is a possibility whether you wanted to read and write operation to do it for slave mode or to do it for the master mode. So whenever you put this as a 1, it is nothing but condition, if at all it is a slave mode, it is in the read mode of operation, and if it is 0, then it is write mode of operation. Whereas in for the master conditions, putting this, it is completely reverse of that of the slave. So 1 indicates the transmission is in process, whereas in 0 indicates that transmission is not in process indication. Next is UA bar. So UA bar is nothing but unique address generation. So this is 1 indicates is nothing but user needs to update the slave address using the SSP add register. So the slave addresses has to be mentioned under the SSP add register. So under which you can specify your multiple slave address using this. So 1 indicates is nothing but user needs to update the slave address, and 0 indicates nothing but address do not need to get updated. So this is the condition of it. And the last bit is buffer full and empty. So whatever the data to be transmitted and received, condition will be there whether buffer is full and empty. That status will be indicated by BF bit. Next register is SSP-Con1 register. This SSP-Con1 register WCOL bit is nothing but write collision bit. So this write collision bit in master transmission mode 1 indicates that to write SSP buff register in the I2C conditions. So in order to that, if at all there were no any kind of valid transmission to be initiated, in that manner it will be initiated as a 0. So in that manner, 0 indicates no collision, 1 indicates there is a collision between your whether the transmission is initiated, and again before the completion of that particular transmission, still some of the data will be there for transmission. So there is a collision between old data and new data. So to make an attempt while in I2C condition is not valid for these kind of uh, overlapping of that respected data. Now same collision will be in the slave transmit mode. Again SSP buff register is written while it's in still transmitting your previous word. At the time this bit will be 1 and this bit will be 0 in slave mode. That will simply indicates that there is no collision under the mode of reception, under the slave mode. Next is SSP OV bit. So in that manner, this in master transmit mode, a write to the SSP buff register that was attempted to write while I2C conditions were not valid for transmission. So in that manner, again overlapping and non-overlapping will be considered into it. So 0 indicates no collision, 1 indicates that there is overlapping. So similar to that, again a slave transmission condition will be notified it in terms of overlapping and non-overlapping. Now SSPEN, to enable your MSSP module under I2C mode, you have to utilize this SSPEN, where you will specify this particular SDA and SCL register. So which will simply disable the SDA and SCL, and while putting this bit as a 1, is nothing but enabling this SDA and SCL 2 lines. Next is CKP bit. So in slave mode, this will release clock, and when this bit is 0, it will simply holds your clock. So it is used to ensure that the data setup time before the communication. So you require these kind of setting using CKP. And under this particular, under the master mode, this bit is not utilized in the master mode. Last 4 bits are nothing but mode of operation. So this mode of operation is nothing but I2C slave mode of operation. So in order to that, if you put these 4 bits as a 1111, then 10 bit addresses are initiated with start and stop condition with an interrupt enable. If you put these bits as a 1110, it is nothing but you are initiating I2C as a slave mode with 7 bit of addresses. So the address generation, be it with the 10 bit address generation and 7 bit of address generation, these 4 bits will help you out in order to set the particular 7 bit and 10 bit address generation. Along with that, if you utilize the condition of 1011 to these 4 bits, in that manner it will simply controls your I2C under the master mode, and in that manner your slave must be idle. Then and then only you can utilize this. And when you place this as a 100, then you will be enabling your I2C as a master mode, but to provide the clock. So all the time for this communication, if you place this as a 1000, in that manner the clock condition will be clock equals to FOAC divided by 4 multiplied by SSP add plus 1. So like this way your clock becomes flexible in order to utilize this under the 1000. So if at all you don't want it to utilize standard clock frequency of let's say 400 kilohertz or 1 kilohertz, that is given more specifically, in that manner you can utilize by using this formula by changing the clock. Next, again to set these kind of 10 bit address generation and 7 bit address generation to the slave side. This was from the case of the master mode, but if at all you wanted to set these two addresses from slave side, these 2 bits, these 4 bits will be utilized as a 0111 and 0110. So MSSP control 2 register, which is also known as a SSP con 2 register. Now this SSP con 2 register can be utilized under the master mode and slave mode. So in that manner, very first bit under this is a general call enable bit. Now this particular general call enable bit will help you to utilize this particular in only slave mode. So this will be particularly bit will be disabled under the master mode. Whereas in for the acknowledgement status, so this acknowledgement status bit is nothing but you can set this bit as a acknowledgement status bit from master transmit mode. If you put this bit as a 1, then acknowledgement will not be able to receive from the slave. And when you put this bit as a 0, so in that manner you can say that acknowledgement was received from slave. So to know the status of your acknowledgement, this bit should be activated. Then and then only you will able to receive rather than you, master will able to receive acknowledgement from slave. So for that purpose, it is required for the enabling the acknowledgement status. Next is acknowledge DT. So this DT is nothing but data bit. So in that manner, this acknowledge DT bit is nothing but master receive mode, it can be used. So only master receive mode means your slave is sending this for the data acknowledgement. So indication of your data acknowledgement from your slave transmission. So in that manner your ultimately master becomes under the receive mode. So this is the status bit for acknowledgement, for knowing the whether you will be able to receive the data or not from the slave. So in that manner your slave should able to indicate this in terms of acknowledgement. So that is nothing but acknowledge DT. Next is acknowledge enable sequence bit. So this acknowledge sequence bit will be initially can be loaded with the initiate acknowledgement sequence of on your SDA and SCL pins. So in that way all these particular acknowledgement will be able to initiate and transmit your acknowledged DT data bit by hardware on these two lines. So if at all you have disabled this particular bit, then it will be considered as acknowledgement sequence will be idle. So this is the indication where you could able to judge upon for the all the acknowledgement are able to receive on SDA and SCL pins or not, along with the acknowledgement DT bit. Next, RCEN bit. RCEN is nothing but receive enable bit. Now this receive enable bit will only be enabled for master receive mode. So in that way, if you put this bit as a 1, it will simply receive, enables the receive mode for your I2C. Otherwise, it will be idle. So in that manner, no reception will be enabled. So for your master to receive any kind of data from your slave, this bit has to be taken care into consideration. Along with that, if at all you wanted to check the status of that particular data bit on SDA and SCL, this bit has to be enabled. Next is PEN. PEN is nothing but stop condition. So in order to that, you can able to start and stop condition. In that manner, PEN bit will help you to initiate stop condition on SDA and SCL pin. So in order to that, you can able to initiate the stop condition on the two signals, maybe the SDA and SCL. And when you put this bit as a 0, ultimately that condition will be considered as a stop condition. So there is a stop condition is idle, or there is a stop condition is initiated. So these two cases will be there for your PEN signal. After that, there is a RSEN signal. This RSEN is nothing but repeated start condition bit. So it will simply initiate the repeated start condition on your I2C signals or I2C pins. And in that manner, if you don't want it to repeat the condition from that same slave, in that manner, you can disable this bit. So if at all you have master is only fixed with one particular slave, let's say slave number 7, and continuously he'll be in the reception mode or transmission mode, and in that manner you need to repeat the again start condition for the further more data access from your slave to the master. So in that manner this RSEN bit will be used. Next is start condition. So there is a stop condition, likewise there is a start condition, and in between them it is a repeat condition. So start condition similar to your stop condition, it will initiate the um, uh, particularly enabling the start status from your master side, and like that way you can disable this status by putting this value as a 0. Along with that, one more register is used, and along with that, one more register is used, and that is SSP add register. This SSP add register, you are going to load the address for that particular uh, um, slave. So that will be on the basis of whatever baud rate will be specified for your I2C clock. Based upon that, you can evaluate address of your slave. So in that manner, the formula which is given as FOSC divided by 4 multiplied by I2C clock, whole of the thing minus of 1. So through this you will able to have one kind of decimal value. If you put all these values all together, then to after the formulation or calculation of this particular values inside this formula, you will able to define one decimal values, convert that decimal value into hexadecimal, and you can load that particular address into the SSP add register. So SSP add is nothing but your slave address, and that will get masked with the help of the mask bit under the case of the I2C, and in that manner your exact communication from your that respected master to that slave will be enabled. So this was all about your I2C. So in order to that, you can further move ahead with the I2C initialization for the application interface. Uh, 5 different steps are required. Now, in that manner, if at all you wanted to program this MSSP module under I2C mode, you need to configure SCL and SDA pin through trace register. After that, we need to calculate baud rate for your slave address. So all the kind of slave address in the respect of, let's say, if at all standard clock for I2C, it is taken care as a 100 kilohertz. So for this particular 100 kilohertz, FOSC is, let's say for example, it's considered as a 48 megahertz. So for this I2C clock and for the standard system clock frequency, by putting all those value all together, you could able to generate the slave address. So this particular formulation, computation of this particular formula, you will able to get in decimal value, convert that decimal value and into the hex, and that hex value has to be loaded in SSP add register. Third step, if at all you wanted to enable master in I2C mode, you need to require SSP-Con1 register. In order to that, you can utilize this as a I2C master mode. So through that, you will be able to enable the master mode. After that, you will simply disable this slew control by setting up this SMP bit in SSP start register in baud rate selection. So in order to that, you will be utilizing this standard 100 kilohertz as a clock control for it. And the last, you will enable the SSP-Con1 register by putting the SSP-EN bit, so that your I2C mode will be enabled. So like this way, you will able to initialize the I2C mode in master. Next will be the initialization of the same kind of, if at all you wanted to write I2C mode under the respected condition of the I2C initialization under C. So in order to that, all 5 steps has to get converted in the form of the statements. So let's consider this as a direction setting for SDA and S clock. After that, keeping the condition of your SMP bit, in order to that you are disabling and enabling the clock skew control for the high speed of mode of operation for I2C. After that, setting up the clock for your SSP add register. After the calculation for this particular 100 kilohertz, you will be able to generate one hexadecimal value, and this particular hexadecimal value will get added in the SSP add register. And after that, you will enable this MSSP module. So like this way, you will be able to initialize your I2C module under this particular I2C mode of operation.